STEM and revision video here again for physics. We're going to be doing particle physics with our special guest, Eamon Byrne. Good to have you on the show,
Thanks for having me.
Okay, I know we haven't done a lot since Christmas and that, and we haven't done any biology or chemistry, it's been pure maths and physics, but I do believe that I just don't like biology, and it's sort of girl subject, so essentially I'm just going to jump right into it with this particle physics with Eamon.
So I'm going to go through different types of particles there are leptons. This is a fundamental particle and cannot be split. There are hadrons. This can be split into mesons and baryons. Mesons are made of a quark and an antiquark pair, and baryons are made of 3 quarks or antiquarks.
Okay, so what we're going to do is we're going to explain the particles here. So leptons are quite small particles, so they're like a 1/2000th the size of a proton, and so they are only subject to a weak interaction. And so a weak interaction is caused by the W and Z bosons, types of force particles. Hadrons, however, are bigger, and so because they're made of quarks, which are also bigger than leptons, they're affected by strong interaction, which is the gluon with the symbol G. On top of that, so I'm going to draw the particle grid, the standard model of all the particles. Since we know the mesons and baryons, they're made of quarks. Okay. Quarks are types of fermions, which is just mass particles instead of bosons. So you've got up quark, down quark, charm quark, strange quark, top quark, and bottom quark. Top being quite unstable and big, and up being the smallest. So each of these have half a spin. The charge is, I believe, plus 2/3 and minus 1/3 for the bottom ones. Strangeness is quite strange, right? It has a strangeness of -1, whereas an anti-strange quark has a strangeness of 1, and that's quite big in physics. Aside from that, they each have a baryon number of 1/3, which is always conserved in reactions. As for leptons, you've got the electron, the muon with the symbol mu, Greek symbol, tauon, symbol tau, muon neutrino, a lot smaller, massless, electron neutrino, muon neutrino, and tau neutrino. They each also have a half spin, charge of -1 for the tops and 0 for the bottom. They said they're massless, they're not really massless, so it's really small. Each have a lepton number of 1, which is always conserved as well. As for the bosons, they're all types of fermions here. So bosons, much smaller. Some people believe the fermion is massless, and so you've got the gluon, strong interaction. The photon for electromagnetic interaction, infinite range, not as strong as a gluon. Weak interaction, and the other type of weak interaction, the Z particle. They each have a 1 spin, I think, no charge, apart from the W boson, it can be plus or minus depending on which one it has to be. So strangeness is always conserved unless it's a weak interaction involving leptons in the equation, and that is the standard model of particles.